admitted most people into the webinar. So I'll just kick things off. Good afternoon. My name is Ryan White. I'm with the APA New York Metro Transportation Committee. I'm also the transportation planning lead for Jacobs in New York and New Jersey. But on behalf of the APA committee, I just want to thank you for attending today's panel about pedestrian modeling. We're excited to see that so many people are interested in this topic. For those that don't know, pedestrian modeling helps simulate how people move through streets, transit hubs, and public spaces so that we as planners can identify choke points and potential hazards before construction or even a policy change occurs. And there's many tools to do this. And our great panelists will talk more about that, showcasing, how they use macro, meso, and micro level approaches. You're going to hear from five panelists for the first hour, and then we'll leave 15 minutes at the end for Q&A. But we do encourage you to just add your questions into the chat, and we'll try to get some of those at the end. Our panel includes Carissa Lidstrand, who's the planning lead at New York City's Department of Transportation. Andres Sefsuk, director of City Form Lab and the head of City Design and Development Group at MIT. Dong Gao, who's a project manager at HNTB. Elizabeth Jewel Gludon, who's a transportation operations lead at VHB. And finally, Sam Sklar, who's a senior transportation planner at Systematica. So with that, I'm going to jump right in and turn it over to Carissa to talk more about the planner's perspective on pedestrian modeling and hopefully answer questions like, what is it? Talk about New York City DOT's roles in pedestrian modeling. And I think how a new program may be rolled out in the near future. So with that, I'll turn it over to Carissa.
All right. Thank you, Ryan. Hello, everyone. My name is Carissa. I work in the Public Realm Unit at New York City DOT, and I'm just going to give a brief overview before handing it over to the panelists to talk about specific pedestrian modeling software. So first, I'm going to get into kind of what is pedestrian modeling. Really, it's a tool which identifies what route people might be taking and then how many people might be taking that route. So on the map on the right-hand side, you'll see kind of a starting point, point A at a school. And then if you're walking up to the park, point B, there are several different routes that someone might choose to take. And the reason that they might be choosing this route is due to a handful of reasons. It could be, what is most comfortable for people? Are there a lot of cars on that street? So maybe they're choosing not to take that route because of that. Are there a lot of trees? Does it have to do with how many turns you have to make? Really, you can get into kind of all these details with different levels of pedestrian modeling software, which can range in different scales from citywide all the way down to a specific transit station. And so there's also a lot of ways that pedestrian modeling software can be used. Really, it can be used to start to think about our sustainability goals and mode shift, really starting to think about along a corridor how we're prioritizing different modes. On the picture on the right, you can see this is in New York City. We expanded the sidewalk to accommodate more pedestrians in Midtown Manhattan. And so starting to really think about the different modes that are using the street, whether that's pedestrians, cyclists, bus riders, or vehicles. And it can help us start to prioritize both where we're wanting to do work, but also just kind of understanding those modal priorities and any policy changes we want to advocate for. And so pedestrian modeling does have some limitations. It really depends on the type of software you choose, and our panelists will get into kind of those details today. The models are really only as good as the data you're providing. If we're only looking at commute-based data for pedestrians, we're losing out on that nuance that different leisure trips can come into play, or kind of those smaller trips that people might be taking to go to the grocery store or to walk your dog or different things, because pedestrians can have a much smaller footprint than other modes do. And then there's kind of the cost piece of things too. If we're collecting volumes citywide, that's going to be really expensive. And so are there other ways that we can be collecting data that might kind of limit the cost? And so now I'm going to transition into how New York City DOT is thinking about pedestrian modeling software. Starting with in 2020, we set out to create a comprehensive pedestrian plan for New York City because we were realizing that we do not have a current plan that thinks about and prioritizes pedestrian infrastructure. And so we created the pedestrian mobility plan, which categorizes the streets into 5 different categories. This is just based on land use, and so it's not a route choice model. We also have our biannual pedestrian counts. We collect these at over 100 locations citywide, and this has been going on since 2007. We also have our citywide mobility survey, which really gets into a lot more details and nuances of kind of pedestrians trips throughout the day. So it's not just commute-based trips, but also kind of leisure trips. Anytime you're leaving the house and doing something, we have that granular data. And then we've also been looking into piloting different computer sensors throughout the city. So we have about 17 right now. And so this is one way that, we're thinking about how can we transition from like not collecting volumes like citywide, because that is very cost prohibitive, and thinking about how sensors can help us in this endeavor. And so currently the way that we're using the tools that I was just explaining on this last slide are both in project development. So thinking about, where do we want to be working? Where are there a lot of pedestrians that we want to, think of some different strategies to increase the modal share on a street. We also use it to advocate for policy changes and also just have conversations with other city agencies, since everyone is interested in using space on the sidewalk. We really want to be thinking about, what do we want our sidewalk and even our streets to look like? And then also with the biannual pedestrian count, since we've had that information since 2007, we can also start to understand trends and where there's been some like increases in pedestrian volumes or even declines in pedestrian volumes and investigate that further. And so there are definitely some limitations to the current data sets that we have. So the pedestrian mobility plan, as I mentioned before, is mostly about land use. So it's not a route choice model. And so that's something that we would be interested in exploring more, is how do we start to pinpoint the routes that people are most likely taking to get to the park or to get to the grocery store, and start to incorporate that into, where we're prioritizing projects. And then also with our current biannual pedestrian count system, we actually hang cameras, we have to get permits, and then we have to count all of the pedestrians manually. So that's where kind of increasing the amount of sensor locations that we have throughout the city could be beneficial, so that we don't have to do all of that labor that's included in the current count system. And so some of our next steps, as I was mentioning, is to potentially expand our sensor program. We would love to get at least 100 computer vision sensors across the city. And then we've also been collaborating with Andres, who's here today as a panelist, on a citywide pedestrian model for New York City. And so with that, I'll pass it back to Ryan.
Yeah, thank you so much, Carissa. That was great overview as to, how you're thinking about these issues at New York City DOT, which is great. And it's exciting to see the changes that are coming up. So yeah, I'd like to turn it over to Andres to talk a little bit more about it. He's with MIT, and he'll talk, I think, about, macro modeling and how we can use that to help plan. Andres?
Great. Can you see my screen okay?
Yes.
Excellent. Well, thank you first to the APA NYC NYC or NY Metro committee for putting this together. It's really great to see the initiative, and also thanks to Carissa, I'm a huge fan of NYC DOT pedestrian work. To my knowledge, it's the only city planning agency that actually has a pedestrian unit in it in the US. So really grateful for that collaboration. So I'll share some of our ongoing work on modeling pedestrians in cities, and I'll show the case of New York in particular, but also reflect on some other instances. I'll just start by saying that as Carissa nicely already demonstrated, pedestrian counts are often available from a certain number of streets in many American cities. But one of the benefits of modeling pedestrians using that data is to expand or extrapolate that information with models to a whole city or district and have a kind of informed understanding of how many people walk on all the streets. I think this helps allocate resources and plan better in such ways that the investments we make will actually impact people who walk. And I'll try to show an example of how pedestrian volume information can also be critical for understanding how pedestrians face hazards in the city, whether it's traffic crashes or heat or noise, air pollution, and various other hazards that exist. And finally, I'll reflect using another example how the models can actually help us understand how changes in the built environment, whether they are changes in street infrastructure or changes in land uses and urban form that affects the origins and destinations of pedestrian movement, can change foot traffic in cities, and how we can use models to forecast those changes so that we can actually incorporate models into planning. So I'll talk about the urban network analysis framework that my team has been building over the last 15 years or so, that are available both as a Python package, open source. We're constantly actually working on improvements, and we'll be releasing a new version this year, as well as a plugin for Rhino 3D, which is a desktop software that a lot of designers and urban designers use. The overarching framework involves 5 steps. As with all models, we start with data collection, and that involves information about both travel behavior, what assumptions do we put into the model about how people behave as pedestrians in the city, potentially person characteristics, the different demographic groups in the model, and critically, the built environment where behavior takes place. So the travel behavior data typically comes from various travel surveys, whether they are city surveys like the New York City-wide travel survey, or sometimes also other sources like the American Time Use or other custom surveys. And this fills the assumptions that the model has about pedestrian trip generation, destination choice, distance decay, route, whether we base all the routing on distance minimization or use generalized costs that take into account the different characteristics of streets, as well as route choice preferences. In the case of New York, our team actually put together from various sources, starting with the data that NYC DOT had available, but then really consolidating it and then filling in the gaps where data didn't exist for a citywide pedestrian network. So this is a network we assembled covering all 5 boroughs, where the network topology was humanly verified against 2019 aerial imagery. And it's been tested for routability and so forth. So as far as I know, this was the first routable, at least first open routable pedestrian network for New York. I know Google has been working on their own efforts, but those tend to be closed source. And then we assembled a lot of data about different residential locations, business locations, schools, metro, open spaces, jobs, companies, and so forth. Once the data sets put together in this framework, we proceed to conduct preliminary pedestrian trip estimations. And so the previous data serves as input, and I'll show a couple of examples. Here, we have one census block, which is illustrated by these 4 blue points. Instead of assuming that trips originate at the centroid of the census block, we typically find the frontages of the census blocks and distribute the amount proportionately to the frontages. So, in fact, the census block has 4 sides, so it produces 4 frontages. And in this instance, I'm just showing trips from a home location, which is 1 census block, to the very nearest subway stop. But it illustrates a couple of important things. One is that we can assume that people don't necessarily take the shortest path. We typically find many possible paths that people can walk. In this instance, the detour ratio says that we find all paths that are up to 15% longer than the shortest available path. There is a certain distance decay assumption about how the likelihood of walking drops with distance. There is a cutoff radius, and there's a destination choice model. As you can see, not all trips go to the nearest subway entrance, but in fact to both subway entrances with a certain probability. So there's a model behind that. We can then expand this to multiple subway entrances that are available or accessible within about a half-mile walkshed. And again, the destination choice model finds the probabilities of how likely trips go to different destinations that are available within the catchment based on both their proximity and also their attractiveness level, which can be controlled by a number like level or headways or daily service or number of subway lines. And then this is expanded to a citywide scale from all census blocks to all subway entrances throughout New York, producing a sort of estimation of one particular type of trip, which is home to subway type of trip. And that logic is then repeated or expanded to many origin destination pairs. So we estimate trips between homes and subways, homes and bus stops and amenities and schools, but also trips starting from schools or jobs or transit locations. So there's a matrix, an OD matrix of trips, and each one is basically described in this pairing table that we feed into the model, and each kind of location, whether they're homes or jobs, has a location dot file. The locations are represented as points, usually at the address level. And so that produces different kinds of flow estimates across different trip types. I'm not going to show all of them here, but these are 3 instances of different trip types, from between businesses or retailers and service amenities in the city, between homes and those amenities, and also between homes and jobs, all with specific assumptions. So once those are estimated, and usually there's perhaps a dozen or 2 dozen trip types that are estimated, the model is then calibrated on actual pedestrian counts in the city. So we rely on real pedestrian foot traffic data from the city. In New York, we actually were fortunate to have quite a few locations, so over 1,000 locations on weekday peaks, and about half of that on weekends. And we use these actual counts as ground truth, and then fit the model estimates through a calibration process to best match these ground truth estimates. So this is the illustration of that result for the New York first phase of the New York model, where on the upper chart here we see the training data fitting, which as you'd expect typically produces very high correlations or fits, so close to 98% here. But this is because the model has seen that data, so it's trained on that data. But on the held out data, which is the model has not seen, the accuracy is slightly lower, but still above 80% in each case between model estimates and actual foot traffic at the locations, and we estimate the different statistics for that. And so altogether that produces a calibrated fitted model for each time period. We have a model for morning, midday, and evening peaks, and also the same for weekends. So this is an example of a fitted evening peak model. If I zoom in here to Midtown Manhattan, then you can see that the blue labels on the map that zooms in illustrate the actual counts by New York DOT of pedestrians on the different segments, and then the white labels are model estimates on the calibrated model for the same streets or segments. They're not exactly the same, but they tend to be pretty close. Across all time periods, the model estimates and the counts, including both training data and test data, is over 90% correlation in all time periods. Finally, when we have a calibrated model, what can planners do with that? Once we have these estimates of foot traffic on all the streets citywide, I mentioned earlier on that one of the applications is that you can use the estimates as denominators for various hazard data. And I'm just showing one quick example of that here from this New York study that we're working on. These on the map here are the 100 worst intersections in terms of pedestrian crashes with vehicles in the period of 2012 to 2023. But this is just counting crashes. Now, if we normalize these counts, we start obtaining pedestrian crash rates, which takes into account how many people actually walk on each street. And so if each crash count is divided through by the number of pedestrians on that intersection, we obtain a very different picture. In fact, Midtown and downtown Manhattan are no longer even in the top 100. Many other parts of the city have worse crash probabilities when we account for people actually walking on those streets. So this is highlighting places where the crash risk per pedestrian is highest, which tends to be much bigger in Eastern Brooklyn or Bronx, Queens, even parts of Staten Island. And I also mentioned that one of the applications is to forecast how changes in urban design or the built environment and infrastructure can impact pedestrians. So I'm using an example from a different city to illustrate that, because we haven't done the work for New York on this yet. This comes from a model we built with the American University in Beirut for the city of Beirut. And long story short, we calibrated a similar type of model for central Beirut as in New York. And then we held a participatory design workshop, which was addressing the recovery after the Beirut blast of 2020. If you have maybe heard in the news, there was a massive explosion in the port of Beirut, devastating neighborhoods around it. So this workshop involving around 60 participants from city government, neighborhood associations, companies, universities, etc., came up with a series of proposals of how to improve the streets and neighborhoods around the blast. Those proposals were summarized as scenarios for urban design and planning, specific improvements, and then translated into scenarios that our research team put into the model that was developed for Beirut. So we were able to use the model to forecast how the design changes that were proposed would impact foot traffic, pedestrian trip generation and trip distribution around the areas. So this chart here shows the forecasted changes in foot traffic area-wide for this district between the different scenarios as compared to the baseline. And these maps here show the spatial distribution of one of the scenarios. So the left side map is the baseline foot traffic that we estimate currently, and the right side shows the change in foot traffic that would likely occur as a result of these urban planning and design changes, with the blue lines indicating additional pedestrians and the red lines indicating fewer pedestrians. So I'll just conclude by mentioning that there are actually a whole range of interesting applications for pedestrian models. Not only do these models show citywide foot traffic, but they are models. Therefore, we can change assumptions and use them to forecast what would happen. One of the interesting and timely applications we've been working on in Seattle is to optimize where sidewalk improvements ought to be located in a way that we would estimate how each sidewalk improvement improves pedestrian accessibility to a basket of daily destinations in the city, in order to locate and prioritize sidewalk improvements that unlock the most accessibility gains first. So it's basically an idea to reconfigure the queue of sidewalk improvements in such a way that we prioritize the most impactful improvements right away. Similarly, we've been...
I think we got to give you... Sorry, just I think, yeah, Andres, maybe just one more minute?
Yep, I'm almost done.
All right,
yeah.
Thanks.
There's this idea that Carissa already mentioned about traffic impact assessments, I think, or mode shift. So a lot of development projects face traffic impact studies, which predominantly focus on vehicular traffic. I think it's time to consider as rigorously the pedestrian impacts of new developments, with the idea of desirably increasing pedestrian foot traffic around projects. And of course, the citywide goals of mode shift entirely depend on individual development pipelines and land use planning and zoning. And so we can, in theory, connect land use planning and zoning to forecasted modal shifts in the city, and use that as a kind of a way to actually guide us to the mode shift targets that cities have implemented. So I'll just lead some of the challenges on the screen, but there's a number of interesting things we can and should do with the models, and we can maybe in the discussion section discuss the upcoming improvements. Thank you.
Great. All right. Thanks, Andres. That was excellent. I appreciate the detail. That was really interesting. I just next want to turn it over to Dong from HNTB to talk more about meso modeling. Dong?
Sure. Thank you, Ryan. And hi, everyone. Dong Gao from HNTB. And Carissa and Andres just show us like pedestrian modeling in the city scale. So what about we zoom in a bit, right? So what if we are looking at a train station, a stadium, or a public plaza? What does pedestrian modeling mean in that context, right? So, as planners, we try to simplify things. So my own understanding about pedestrian simulation, right? So if this is a new concept to you, macro simulation or traffic simulation shouldn't be. That's been around for decades. And if you're thinking about this too, it's quite comparable. It's basically like transporting vehicles or pedestrians between different origin and destination pairs, and they follow different algorithms, and there are different professional softwares to do it. And for traffic sim, very simplified put, it's really like static assignment, dynamic assignment, try to assign vehicles between different OD pairs. There are different softwares like PTV Viswalk, Amazon Transmodeler, sim traffic to help us to do it. And for pedestrian simulation, how do we assign people between different OD pairs, right? So I think two things. The first thing is really shortest path, because people are lazy in nature. We always want to try to find the shortest path between your region and your destination. And while you are walking the shortest path, what if you hit like an obstacle? Like how you navigate that? I think that's when the gravity model, or we call it social force model, kicks in. Think of you are a pedestrian within a simulation setting, right? The destination basically works as a pulling force, try to pull you towards your destination, and all the other obstacles like columns, crowding is basically functions as a pushing force, try to push you away from your destination. That's how a pedestrian navigate within a pedestrian simulation setting. And there are some professional softwares, Bentley Legion, PTV Viswalk, Pathfinder, Mass Motion, AnyLogic to help you to do that. So here's the what. This is the how. As I mentioned, it's quite similar to traffic simulation. So it's following the same existing no build condition workflow. We start with existing pad model. We validate and calibrate it, and then we move into no build. Compared to existing no build, your ridership growth and your geometry doesn't change. And then you build the no build model, and then you move into the build model, where it's going to be same demand as the no build, and your geometry is likely to change to test out design items. And we usually compare the results between no build condition and the build condition. Here's the what, how, and here's the why. Why we do path simulation? I think the biggest thing is really code compliance and requirement compliance. When you design something, you need to design it to certain code. And there's also basis of design to require the design to achieve certain threshold. So that's the first thing. Second thing is pedestrian simulation is a great visualization tool to evaluate design alternatives and enhance customer experience. You can literally put pedestrian and also your design alternatives in the PathSim and show it in 2D, 3D setting. It's a great tool to do public engagement and show it to decision makers about your design proposal. And the last thing is, when you compare build versus no build, there's always like a travel time save, and we convert that into a monetary value that's going to support benefit cost analysis and support future decision making. And in terms like pedestrian simulation applications, I can think of really like two folds. One is normal operation. That means, the space functions as it designs to be, like how it functions in a normal condition. And, in this setting, we usually evaluate the space using free level service, which I'm going to show you in next slide. And another application is really under the emergency egress. For example, what if there's a fire in a station? And if it's a station setting, usually the governing criteria is NFPA 130. And if it's like an airport or a stadium, there's other applicable criteria. So now you know the what, how, and why. Here is some of the evaluation matrix, and I think the most famous one is free and level service. It's similar to traffic simulation. I think it's evaluating based on density and quite similar to the freeway level service concepts. And the criteria is different for different space. Walkway, queuing area, stairs, because when people are in the space settings, they perceive the space or the people surrounding them differently. If you're in a queue, you don't mind if people are standing a bit closer to you versus like if you're just like in the hallway. And the one to the right is really just like a level service map, and we already do this like in 15 minutes, just export the peak 15 minutes. A bit more evaluation matrix. The one on the left is space utilization plot. It basically plots people's natural paths. This is pretty useful when you're trying to plan the space. You don't want to put like a vending machine in people's natural paths. You want to place it somewhere so it's not impeding the natural flow. And to the right is a timed egress. It's basically the darker the color, that means like that space is going to be evacuated the last. So this corresponds back to the ANFPA 130. If you're in the station setting, there's usually like 4 minutes, 6 minute test. So those are the evaluation criteria, and two quick examples. The first one is Farragut North. This one is in DC. So we have those three stations, Farragut North and Farragut West, on two different metro lines. And the metro center is a big transfer station. The client, WMATA, wants to make station improvements within those two Farragut stations, and they also want to build like a pedestrian passageway to facilitate transfer to alleviate congestion at metro center. We did a quick pedestrian simulation for this. This is looking at the Farragut North. Those two are the no build condition. Those two are the build condition, and in the no build AM, because we are adding more stairs, escalators, so people can get faster from the platform to mezzanine and street level. So you will see some congestion relief on the platform level. And then in the PM condition, because the additional improvements is going to take space from the platform, and also if we're building a passageway, it will have like induced demand. So in the build condition, it actually works a bit in the PM condition. So now let me switch back, and I will show you a quick video for that simulation. Just bear with me. It's really quick. Everyone can see my screen, right? So it's basically, the green dots, red dots, the pedestrian are moving. It's in a 2D setting. So, people getting off the train, they're trying to, through the stairs, escalators, get to the mezzanine level, and then passing the fare gates, exiting the streets. All right, let me switch back. All right, another example, a bit more close to home. So it's in New Jersey. This is the MetLife Stadium, and this is the American Dream Mall, and there's a path bridge connecting those two over Route 120. And during post game events, there's always like congestion at the pad bridge at the stadium set, and the clients wants to add another pedestrian bridge adjacent to this to alleviate congestion and also prepare for FIFA 2026. And we did a quick pedestrian simulation model in Pathfinder. This is basically a screenshot from Pathfinder and to quantify, like, if we're building another bridge, how it is going to affect pedestrian flow, and if we're freeing the bottleneck on this end, will it impact anything on the parking garage operation on the American Dream Mall side? Unfortunately, I cannot show anything. It's under NDA, but I'm happy to report back. The other pad bridge is currently under construction. But I do want to show you something like really quick from Pathfinder's website. So you'll have a taste what it looks like. So you can build the thing like in 3D, and Pathfinder is, I think it's really great doing egress analysis. With an FPA 130 timed egress, and also if you're like an architect, or like an FPA 130 is like much more than that. There's also like tenability study, and if there's a fire, there's a smoke, and the pedestrian can interact with the smoke if the fire reaches to you, if the smoke reaches out to you, something like that. So it's pretty powerful. All right, so let me switch back to my presentation.
And we've got about a minute left for you, Dong, just to mention.
I'm
Is that
done.
okay?
This is the last slides, and
Amazing.
it's really like, thank you for the transportation committee to have me, and I do want to apologize to the audience and to the final panelist. I have to jump early. I have a project interview right after this. I couldn't stay for QA. But this is my contact info. If you have any questions or anything, feel free to shoot me an email. Thank you so much.
That's great. Thank you so much for doing this. We appreciate it. Certainly learned a lot. Thanks, Dong. All right, so then I'll turn it over to Liz from VHB to talk about, I believe, micro modeling as well. Liz?
Hi, everyone. Yes, happy to be here. Let me just make sure I'm sharing my screen okay.
Yeah, we can see it.
Okay, great. Let me just start the deck. All right. Hi, everyone. My name is Liz. I'm at VHB. I'm a transportation operations lead in our New York City office. And thank you to Dong and others for kind of setting the stage in terms of, overall framework. I'm going to do a little bit of a deeper dive on the application of a tool specifically using Viswalk. So before I dive in, I just want to talk a little bit about what is Viswalk. Like Dong mentioned, it is a tool that does use the social force method. So it really simulates pedestrian movements based on forces. So things like, repulsion from obstacles and attractions to certain destinations. Pedestrian walking behavior is not super similar to traffic in the sense that people don't necessarily stay in their lane, so to speak. So it really considers the psychology of the walking behavior in the algorithm. And it's a tool that's really suited for public spaces, such as, like you said, train stations, airports, scenarios for event management, really anything that experiences crowding or dense urban settings. And it really has the ability to handle quite a high volume of pedestrians in a single model. So things such as ticketing at an airport, queuing, bidirectional flows that conflict, these are all handled very well and effectively in Viswalk. And one of the best features, I think, in Viswalk is that it has its integration with the rest of the PTV group suite. So this means that things like PTV Vism, which is heavily used for traffic microsimulation, as well as just overall multimodal interaction. So things like public transport elements, such as buses and rail, as well as bicyclists. And it's also compatible with other formats such as CAD and BIM for, extensively large models as well. Going into a little bit more about features. So Viswalk, can handle multi-level facilities using a bunch of different network objects. I might be able to go into these a little bit if time permits, but things like obstacles, areas, vertical circulation like stairs and ramps, escalators, elevators, and of course platforms. Measures of effectiveness, so this is like the evaluation matrix that Dong was referring to, can be things such as density, speed, delay, overall travel time, length of queues, and this is really to not only inform level of service, but other user experience metrics such as comfort, safety, accessibility throughout a certain facility. Uh, you know, this can also be reflected or communicated in the form of not just tables, um, but also things such as animations and visual aids, such as heat maps, which I'll go into a little bit. And this is, really helpful in, explaining the results or your findings to stakeholders and other members of the larger community, as well as emergency metrics such as an FPA, like you touched on. And this can be used, I'm going to be talking about the transit station, but this can be used in really a lot of different settings, anything from, testing public realm improvements, signal timing modifications, things to optimize transit planning, and, this can really inform not just an immediate kind of short-term, but also long-term capital improvements. So the project I'll be talking about is also a WMATA facility. This is Roslyn Station. This is located in the Roslyn neighborhood at Arlington County, Virginia. This, if you see my cursor here, it's over here in this purple circle. Can you see my cursor? Just making sure. Great. Okay. Alrighty. And this is an area that is central to a lot of business, shopping, and dining destinations. You can see here that it's served by 3 lines, the blue, the orange, and the silver lines. I'll give a little bit of a station overview for those that may not be familiar. So the station access is predominantly accessed via this street escalator entrance here. There was originally an elevator in between the two, but in 2020, additional elevator capacity was provided across the street. This is a station where the blue line diverges, so there's actually a significant amount of transfers that are happening from the upper platform, which is right. Oh, I lost my cursor. Sorry about that. Which is within view to the lower platform, which is stacked right underneath a cantilever. So prevalent issues include a lot of congestion as passengers transfer from the orange and silver lines to the blue line. And as part of WMATA's long-range plan, they indicated a potential significant increase in growth, about 30% increase in ridership. 70% of those would be just an increase in transfer volumes alone. And so as part of that, in addition to making changes in headway schedules along the 3 lines, they were also looking to make additional improvements to the station itself. So the objective for us was to develop and calibrate a model for the station during the commuter periods to establish baseline conditions, identify areas of low performance, based on those conditions, really inform potential feasibility of improvements that could be easily implemented within the station. We looked at 2 specific alternatives to really address those concerns, understand the cost implications, and prioritize the needs to meet the regional demand, as well as find opportunities to just overall improve station performance, station modernization, as well as address things like accessibility and safety. So this was during 2021 when we started this project. So we were still looking at, the drop in ridership from the COVID pandemic. And so what we had done was kind of approached a 2-step process for calibration. The first step was really calibrating for a day during COVID conditions. So this would be around March 2021. And what we did was really look for things that are dictated by walking behaviors. So things like preferences to escalators, elevators, how people are maneuvering through the station. Is there a preference to stand versus walk on the escalator? Overall functionality and directionality, and things like that, and the spread of passengers along the platform, along the mezzanine level. And then using that, we basically validated a 2021 model using data that was provided by WMATA in terms of volumes, using the headways at the time to closely match our field observations for an average weekday. And then what we did for the second step was to calibrate a model for 2019 conditions, which was when the station is used more heavily. So one thing that was very beneficial in setting up our model was the use of trace data. So WMATA, their system allows for entry fare gates and exit fare gates. So because of that, you're able to really understand the OD pairs that are happening across the entire WMATA system, not just within this train station itself. So the excuse me, the OD pairs are created when people are entering at one station and then using the exit fare at their destination. You're able to identify, if you see in the highlighted columns there, the start and end place for the specific station, the timestamps associated, and you can understand the exact kind of movement type, whether it was a person alighting a platform, a person boarding a platform, whether it was a transfer from one to the other. And so this was, very critical in establishing things like routing decisions for pedestrians and just overall inputs to make sure that we're accurately reflecting, the weekday that we had in mind. So with that, I do want to show a quick clip, and I apologize, this was prepared while I was running the model, so it's not as smooth as I would like, but the ability of Viswalk to conduct more kind of movie-like clips, or that's definitely a feature. So things like vantage views and transitions are all able to be done, for creating an animation file. Here you can kind of see, as people are moving around, the different types of pedestrian types. So there's men, women, there's women and children. You can also include wheelchair users, commuters with luggage, and those all inform on how they take up a certain amount of space. Things like escalator speeds, elevator speeds, and the use of, overall distribution of those are all reflected, in our existing conditions. So you'll see here, like when elevators close, people are assumed to wait until the next elevator call. And like you can see as well, you see the arrival and departure of trains. These are all based on, the actual train arrivals as provided by WMATA. If I can quickly come out of here and show you a little glimpse in the model. This is the actual model in Viswalk. So a couple things I just want to highlight in terms of just overall, user interface. You have your network objects here on the left. A lot of these have to do with PTV Vism, but you can see at the bottom, these are specific to the pedestrian kind of Viswalk capabilities. And the great thing is that if you have a model that really is multimodal, you have the ability to kind of have everything all cohesively in one model.
Liz, we can't see your screen if you're trying to share
Oh, you can't?
PTV. No, we see PowerPoint.
Oh, you still see that? Okay, give me 1 second. Didn't realize I had to. All right, let's try again. Can you all see? Great, thanks, Sam. Alrighty. So like I was saying, the network objects here on the left, it's the beginning is kind of the list specific to the Vism capabilities, and the bottom here are more specific to the Viswalk pedestrian network objects. The other things I'll mention here, you can see kind of the different areas that are shown. There are different colors here. I currently have them by the functionality. So anything gray here is really a pedestrian walking area. A few specific ones are green or red, depending on if this is like a sink or source for the station itself. Things that are pink have to do with, a certain space that's identified as a waiting area for pedestrians or passengers to alight a train. And then the platform is blue for, other way around, sorry. The blue is for the waiting area, and then the pink is for people that are alighting from the platform. And one of the great things about Viswalk as well is that you have the ability to, kind of integrate any kind of plans in CAD as well as PDF. And so the ability to create the station from the ground up, so to speak, is pretty streamlined, as well as the ability to kind of navigate through specific lists of information. So this is very spreadsheet friendly as well. All right, I could keep going on, but for the sake of time, I will go back to the presentation.
And probably about 1 more minute, Liz.
Oh gosh. Okay. Too much fun. Alrighty. Can you see my screen again?
Yep.
Okay, great. So this is just an example of the type of heat maps. Sorry about that. Let me go back to the. the types of heat maps that can be produced. This is really looking at more of an axiomatic view to kind of get a deeper look on the specific areas. Here you can see, for example, the primary flow for the station was exiting in the AM and entering the station in the PM. So you could see these escalators that operate in the up direction. They had a lot of congestion at the landing. And then you would see over here, this is more of a bird's eye view. In the PM, when people are trying to exit the station, there's heavy queuing happening at the street level of the elevator access there. I'll go through this pretty quickly, but there we tested two alternatives. Each alternative really had a suite of different improvements. Things such as like a cantilevered mezzanine, addition of vertical circulation elements along the platform, additional escalator here in between the existing two escalators here. Fun fact, this is the third longest escalator in the Western Hemisphere. So, certainly a lot of people were not walking this and they were riding, this the entirety of the way. And so this kind of shows you the ability to do a heat map comparison between our no build, our what we're calling a low cost and a high cost based on the the suite of improvements. And you can really see, depending on the comparison, where the improvements are more significant. And so things like the landing here, the red that you see for the AM condition, improves by about 2 letter of service grades. Similarly, you see less spatial use of the center of the mezzanine because of the addition of elements happening at the further extents. Again, this is just an example to show the different kinds of grouping of level of service improvements that are here. Similarly, for the PM, most people are entering the station, so you could see things like where there are no improvements stayed largely the same. Like I said, the street level in front of the elevator entrance. However, addition of an escalator here and also improve this by several level of service grades at this fare gate entrance here.
I think we're gonna have to leave it there, Liz. I'm sorry.
That's okay. That's
Just
all
want
right.
to leave time for Sam too.
Sure.
But thank you. That was great. I love seeing those visuals. It really helps. All right, so I'll turn it over to Sam from Systematic to talk about his tool.
Thanks, Ryan, and great work so far, panelists. Can everybody see my screen here?
I think it's load. Yep, now we can.
Okay, let me start the slideshow. So I'm going to do a speed run of space syntax because I want to make sure we have time for questions. So I'm going to skip over the interactive portion where I was going to ask if people had heard of this software/process before and assumed no. So that's me later. So space syntax is a process that's iterated in the software called Depth Map. This is an open source software that you can download from the internet. It's developed by the University College London, and you can spend your whole career trying to figure out the ins and outs of this. So where this differs from my colleagues' presentations is that what we saw from Andre was a statistics and observation-based pedestrian model. What we saw from Liz and Dong was an agent-based model, and what this is more of a topological mathematical model. So what you would use space syntax for here is to model existing movement patterns and try to forecast future scenarios, understanding the relative influence of the 3 key factors here. So spatial layout, land use, and transportation. So here's just a couple differences. I want to take a minute or so to go through what the differences between space syntax and an agent-based model. I think the key point here, the things I want to point out is that this is not a time-based model. You can't predict models over time. It's a static snapshot. It is used best for urban design, so layout evaluation and movement prediction. What you get instead of movement patterns and behavior, you want to understand the difference between how people might use a network based on the angular interactions between nodes and segments of a network. Just a note, theory warning, I'm not going to get into theory here, obviously, but there's a textbook. I'm happy to send this presentation out later with a link to the textbook. The theory will help sort of troubleshoot when there's challenges or a model is not behaving the way you expected. So I wanted to make this particularly practical. So I took a couple neighborhoods in Queens. I took Woodside, Jackson Heights, and Elmhurst, areas where I have particular familiarity and areas where the network was more varied than the typical grid of a Manhattan which shows that people might make specific choices and patterns of movement based on the network shape and design, rather than maybe an agnostic if you're going to turn right or left into the grid in Manhattan. All you need here is a DXF, which is a AutoCAD output, which you can create from your GIS program. So folks have familiarity, you can export your network from a shapefile or geopackage to a DXF. Here's the process of how I went about doing this. I'm going to try to get this as fast as possible. So I chose these 3 networks for the reason I said. I use the OpenStreetMap downloader inside QGIS to download the highway artifacts, but you can also choose the Street Center lines from New York City Open Data, or you can draw a network yourself, or from a client as well. That's fine. 90% of the network of your time should be spent cleaning your data. You want to make sure space syntax is agnostic to changes in here. So you want to simplify your network as much as possible, because it doesn't have spatial awareness or agent-based movements to help calibrate how people might choose. So if you've got 3, 4, 5 different lines representing lanes, it might draw and the gravity of how people move toward those points. Export it as DXF, import it to depth map. And then there's a couple steps here, which is just the process. And again, I'm happy to send this out so folks have a tutorial later. But it's the process of bringing the network into the software for analysis. So here is, I think, the key subject and box you're going to want to take a look at when you are starting your space syntax analysis. It's under tools and segment analysis, and here are the 3 things you want to make sure that you're including. You want to check the box that says choice between this. You want to choose metrics. So because this is the European software, the analysis units is measured in meters. And so if you're doing an American or imperial-based project, you're going to want to convert that into your area of analysis that makes sense for locality. So approximately 800 meters is half a mile, and you can scale up from there. And in that radius box is where you're going to include your levels of analysis. So you can include multiple, but you always have to include N. If folks are familiar with programming, object-oriented, this is the else if. So you have to include your else to make sure it's capturing the entire network. So I want to just give a quick rundown of 2 of the different outputs that you can get here. One is choice, and the other one is sorry, not choice, but integration, and at different levels of analysis. And so what you'll notice, you'll notice some slight changes here. What this is saying is that from any point on this map to any other point on this map, people are likely to choose the route that's highlighted in not necessarily dark blue. So that's Broadway. Folks are familiar with the neighborhood up north there. That's Northern Boulevard, and down towards the bottom is Queens Boulevard. And I want you to just take a quick look at how this network changes as we increase the distance between any 2 points. Here's half a mile, 1 mile, 2 miles, 3 miles, 4 miles, and then infinite distance. And so one of the things you'll notice here is that straight lines and longer segments tend to be more prominent in this model, and it's important to understand that for how people are moving by mode, right? So because you're doing just distance based and not mode based, there's ways to proxy this. So someone might take a half a mile to mile trip by foot, but longer by transit and even longer by car. And so this is an understanding of, do your arterials match up with how people are actually using the road? Do you have a network where people just have a standard grid so they can choose which way they want to go? And where are areas for potential improvements to your network? Or if you're doing a maintenance plan, how might people, and this will link up with sort of the work that DOT is doing. It's the underlying model and representation of how people might choose to move through a place. So here's the differences between choice and integration, which I'm going to get to next. The key takeaway that I want you to remember is choice estimates through movement. How often is any particular segment used for the chosen distance? Integration represents to movement. How easy is it to reach this segment, any other segment from the chosen distance? So I wanted to just do a quick integration example, and I want to leave time for questions. So I use the same scale, but as you can see, as I move through the different distances, you're going to start seeing redder and redder and redder, as it's easy to get to any one of these places from any other distance as you get longer and longer for this particular neighborhood. Basically, what this is saying is that you've got a grid here, you've got your the choice to go to any one of these places is not necessarily different than any other of these places. And so it's just a good test of your grid and potentially how you would want to cluster a retail strategy or understand anywhere you want to put a multimodal hub or maybe a bike share in areas that are the deeper red, as if those might be the most used. So again, I'm going to send this out, and this is my last slide for questions. So I went through this probably quicker than I should have. This is probably not making a lot of sense to a lot of people, but I'm happy to answer any questions. I'm happy to get on a quick call with someone or send emails if people want to talk more about space syntax here. But I want to just reiterate these 5 points. Your network must reflect reality and must be clean to get meaningful results. So this is why I said it's important to spend 90% of your time in GIS or in AutoCAD cleaning up your network. It will not make these connections for you. So if you have anything unconnected, even if it looks connected, it will meaningfully change how how the software spits out choice and integration. If you're looking to do pedestrian only analysis, you can remove limited access highways and other arterials from your network. Space Syntax does not have the classification or cost impedance filter, which is different than some agent-based modeling or statistics-based modeling. Your analysis radius is a radius, and this is something that I've learned relatively recently in this, is that just because you're looking for a 1 mile movement within a boundary doesn't mean all trips are contained within that boundary. You have to extend your boundary at least as far as you're looking to analyze. Just quickly, 2 more points. The calculus, there's a calculus, an understanding of calculus here, that Space Syntax does not handle circles well, because technically the software sees the circle as an infinite smaller vectorized segments. So it will treat your network as a black hole and suck all of the movements into its event horizon. And lastly, Space Syntax does not work for overly large, overly small network and handles grids like New York relatively poorly. Think about a mostly evenly spaced grid and how you might choose to move through it. If you're moving from Midtown Manhattan, say 25th Street to 34th Street, you're likely agnostic which segment to take, and which the network is almost naturally smoothly integrated. So that's me. That's my email. This is where I write about all the stuff, and really looking forward to answering questions. And I'm thankful I can't see all of your faces now because I'm pretty sure you're very confused. Thanks.
That was great, Sam. Loved the sort of different take on this. Very interesting. All right, so I think we'll jump into Q&A. I know we've got about 10 minutes left, and I do think we have some questions, which I'll kick off with this first one. So again, this is for all the panel to sort of address if you'd like, but the question is, can you talk a little bit more about the limitations of performance measures like level of service, and whether these are mainly used to evaluate safety or if there are other considerations such as pedestrian attitudes, behavior modification, etc.?
I can chime in. And I think this is something actually that Andres had started addressing later on in the chat. Uh, I wouldn't say necessarily that level of service is directly correlated with safety. It has more to do with it's kind of a weighted approach of all these other different metrics. But one thing that Andres was mentioning was, you might be in an area that is poorly lit and very little visibility, but it's a level of service A because there's no one there. I wouldn't necessarily correlate that with being the safest place to be in. There is a balance there. I think certainly level service can work hand in hand with safety in terms of making sure that there's enough time for pedestrians to cross, making sure that there is a comfort level there as well, making sure that all demographics, including those with accessibility needs, school children, things like that. I think it's very context-based in that sense.
Great, thanks, Liz. Anybody else want to tackle that one before we move to the next question?
I might briefly just add that it seems to me that LOS is a concept that was really originally designed for highways and arterials, and even though it has, I think, some real applicability in congested situations of evacuation, etc., we really do need better indicators that describe the desired state of pedestrian activity on city streets, and reducing congestion is a problem that, at least outside of transit facilities, rarely ever occurs. And we need to think about, I think, as a community, about metrics that do a better job describing where we want to be.
Yeah, it's a really good point. Um, all right. Next question is, have you had opportunities to test the model's predictions against real-world conditions after a project was implemented? So are we seeing accuracy in terms of what we might have assumed in it, before a project's implemented versus what we're seeing, after the fact? Any thoughts on that? Or
I can chime in with space syntax, which might be a little bit counterintuitive. One of the good things about space syntax, and that is so open source and all GIS and related to that, is that you can draw in your networks. You can, if you're making a change, let's say I've used this for planning a park desire paths inside of large parks in across the world. And one of the things that we have found is that the predictive, you can think of space syntax like a digital version of a desire path modeling in a lot of ways. And so you can go in and predict um, based on how the coloring moves in your two models. And this is a great client tool to allay some fears. And then to your point, yes, we have seen once this is built, one of the changes we built, we have seen that it does match in reality to some extent, right? All models are bad and some are useful, and so that's where I would say the best highest use of space syntax here is for just discussing changes with clients and showing them a visual representation of what some of the statistics or agent-based models might show as well. It's a different third pathway for this type of thing.
I might also add to, Carissa mentioned that New York has longitudinal pedestrian counts now, which is the biennial counts at a 100 something location, 114, I think. It's really important to have longitudinal pedestrian observations in order to do the before and afters. There's a lot of estimation out there that kind of evaluates change without ever checking how good the evaluations are. And I think we all rely on having the longitudinal data to be able to do these project impact evaluations. I put in the chat earlier that we did have actually one study in Melbourne, Australia, where we looked at all the land use changes in the city center, new projects built and demographic kind of residential change and job location change in the city center, and used a model calibrated on 1 year of counts to estimate what would happen to foot traffic as a result of these land use changes. And because Melbourne, like New York, collects longitudinal pedestrian data from the same locations year on year, it was possible to check how good the predictions were. So that study in that paper describes the kind of impact assessment and then validation based on future counts.
Great. Thank you. So this was a question about sort of weather dependency. So what modeling has been done on weather dependency of pedestrian behavior? Someone said, I would imagine that walking is one of the more weather responsive modes of transportation. Temperature, precipitation, night, day, wind, snow, ice on the ground, sun exposure. I guess any thoughts on how weather could impact some of our modeling efforts? Is that part of the process, or is that something that would be added in some way?
I mean, unless somebody else jumps in, again, we often use weather as a variable in the model, and the overall takeaway is that weather doesn't change the distribution of foot traffic geographically very much. It just dampens everything downward. So in rainy weather, we just see less people out. It doesn't have very strong effects on where people are on city streets. And again, that Melbourne study used weather as predictors as well.
Yeah.
I
Overall
can,
network wide. Yeah. Go ahead, Liz.
yeah. I will say there was a project that I did work on, unfortunately confidential, so I can't reveal too much. But you know, um, introducing redundancies, I think, is important in terms of like your design, making sure that, there is some type of weather protecting pathways. That's certainly something that is, I would say, pretty crucial to how people navigate as opposed to, just completely avoiding a certain area because it's raining. So, there are moments where you might see in a model or just just going outside that people might go, maybe at a micro level slightly different direction or path to have a little bit more shelter. So, there's that to consider as well.
Just one last point on that, just to reiterate how different it is. The modeling, weather does not have any effect on space syntax at all because it's not longitudinal and it's not agent based. So I just want to make sure, like I know I would really zoom through space syntax and a lot of it is not necessarily part of a traditional planning curriculum, but you would not use space syntax to try to measure differences in weather movements.
And Ryan, I will maybe just add, I think it's an important concern for a lot of cities now, which is not the rain and the snow, but rather the heat. And we know that heat and discomfort due to humidity and heat actually does have a very significant impact on pedestrians. There's a big literature that's growing as we speak on this topic. And one of the kind of unspoken challenges that many cities face is that while cities have mode shift targets and would like to encourage more people to walk in the future by 2050 or whatever target date, we're competing with weather on those targets. And as things get hotter, and especially during heat waves, that is undoing some of the impacts of good urban design that otherwise would get people out. And so it's definitely a concern. Yeah, I just stop there.
Yeah, no, that's a really good point. Yeah, heat, something to remember that is what we're seeing a lot more of is with climate change. So yeah, good point. Um, Another question is around sort of, autonomous vehicles and micromobility. We're seeing a lot more in this space, and we're just curious if, these PED models could account for increased interactions with some of these new AVs, autonomous vehicles, or scooters, bikes, and shared spaces, that kind of thing. Have any of you seen that in your models?
I haven't worked specifically on a project, with AI integration, but certainly, Viswalk is, like I said, one of those great features is that it has the ability to integrate with different types of modes, certainly with, cyclists as well. So understanding kind of like the a shared space, whether it's an intersection with, excuse me, whether it's like a slow zone, that's certainly something that, can be modeled.
Great.
I would just say that most city DOTs have a priority pyramid. At the top of that priority pyramid is usually pedestrians, followed by either public transit or cyclists, and followed by people-driven cars, and followed by machine-driven cars. And I think it's very important to really take seriously that pyramid and keep designing our streets around the more vulnerable street users and not change our design guidelines to facilitate machines on streets at the cost of people. So I think it comes up a lot in street design and who should the design be for, and I'm a strong advocate that it really should be for people who are on foot, on personal mobility devices or cycles, or those who use public transit.
Great stuff. Thank you. I'm going to jump, but I'm going to turn it over to one of my colleagues here on the committee to tackle the remaining questions, which I think we can wrap up in the next few minutes. But thank you all.
Thanks, Ryan. So we have a couple more questions, and if all the panelists are okay to stay on for a few more minutes, we would greatly appreciate it. So we have one question regarding the technical nature of this work and all the assumptions that they rely on. What strategies, visuals, narratives have you relied on to explain results to stakeholders who are not modelers?
It's a great question. Liz, you were about to speak. Go
No,
ahead.
that's okay. Go ahead.
So some of you may have noticed that space syntax is very color oriented. One of the challenges of space syntax is translating the results into meaningful findings for clients because, like to your point, not modelers aren't looking at the software. And one of the things that I've done is I've translated instead of making it color driven, I've made it line width dependent. So you can export your space syntax findings into QGIS or another GIS software. And I think it's much more, I think it relies on turning what's counterintuitive in the findings into making it as intuitive and narrative driven as possible. So how do you find the story? And I think people respond much more positively in this sense of to relating, a more chosen segment with a wider width of segment rather than a color, because colors have different connotations than widths do. But I think that's one of the key limitations of space syntax is that it has layers of intuition that need to be unpacked, more so potentially than other models where you can show with a great video like Liz and Dom showed.
Yeah, I'll add to that. I think one of the unfortunately I wasn't able to dive too deep into these, but the heat maps I think go hand in hand a very long way with animations because they're telling a more I guess personal story, right? Like if a person has been in a situation where they're traversing an airport, right? They know what it feels like to get on a long queue, and so I think seeing that is a gives kind of a more a deeper understanding as opposed to a table with numbers, and it's all really reflecting the same information, but just reframing I think is really important depending on if it's a community board versus an agency. I think it goes a very long way, and I do think going back to what Sam said about line widths and things, those are all things that kind of can be adapted depending on the audience. The colors usually a lot of people think like, oh, red is, bad. But all of that I think is pretty flexible depending on who you're talking to.
Just quickly, 3 points that one, I think increasingly putting the outputs of the model on a web interface rather than requiring any software. I think it's really important to get more people to read your outputs and get access to what the models explain through simple browsers. Two, using units that are intuitive to people. So for instance, we often use things like people per hour, which is, you can explain what that means on a segment. There are a lot of metrics out there that are very useful and interesting, but have unintuitive units. And so we constantly kind of fight this battle of how do we translate things into intuitive units so people can comprehend what that means. And third, yeah, I think good graphics is important, and especially if it connects to the problems real world problems people trying to solve, so that they're not just sort of additional graphics, but directly illustrate through graphics the benefit of an intervention or change.
Great. Thank you, everyone. And then there's just one last question. It was directed to Andre's potential presentation regarding urban design elements and if they were considered in improving pedestrian mobility, but obviously this can also relate to any other of the software that we discussed.
Right. So in the example that I showed in Beirut, the kinds of urban design changes proposed by the workshop participants that were then translated into the model, they include things like elimination of a parking lane, increase of sidewalk width, addition of ground floor amenities along sidewalks, safer crossings at intersections, adding new destinations like parks that could serve as either origins or destinations for trips. So these sorts of things. But a veritable challenge and an important nuance is that urban design and planning are very complex. There's so many different changes that are impacted on the city, and to be able to translate those changes into numeric attributes of a model is not an automatic or straightforward process. It really does require thinking, and I think we need to probably improve as a discipline the process of how do you take a complex design project and quantify what has changed from the status quo through numeric data in that project, because that's essential for a model. You can't put qualitative information in a model very easily. And so, yeah, that translation, I think, is a key leap.
Does anyone else want to contribute to that question before we wrap up? Okay. Okay, great. Well, on behalf of the APA New York Metro Transportation Committee, thank you to the presenters, Carissa, Andres, Dong, Liz, and Sam, for the pedestrian modeling presentations. We really appreciate you taking the time to share your knowledge with the planning and engineering communities. And thank you, everyone, for attending our event. And we hope to see you at our future webinars. If you would like to reach out to us, please email us at apanymtransportation@gmail.com. Enjoy the rest of your afternoon.
Thanks, everyone.
Thank you all.